Hi everyone, welcome to second help session of the course E220 circuits. Today we are going to solve a few problems. Let's start with problem number 1. I'll read out the problem for you. The charge entering the positive terminal of an element is given by this expression Q equals to 10 sine 4 pi t millicoulomb, and the voltage across the element is given by V equals to 2 cos 4 pi t volts. Now we are asked to we've been asked to compute the power delivered to the element at t equals to 0.3 second and the energy element to the delivered to the element between 0 to 0.6 seconds. Now let's start with part A. We know the power delivered to an element is given by product of its current and voltage. So at any time, P equals to V times I. But in our case, we are given we have been given this Q. So we know current is the rate of flow of charge, right? So we can replace this IT in terms of dq by dt. We can replace this IT in terms of dq by dt, and we can plug in the value expressions for V and Q. Expression for V is this, and expression for Q is this. So what I've done is here is that since charge is given in millicoulomb, so I've used multiply this whole term by 10 to the power minus 3 to convert it into coulomb. And yeah, so here in order to take the derivative of this term, we can take this coefficient term as a common, and for the derivative of sine t, we know the formula based on differential calculus. D derivative of sine at with respect to time is given by a cos at. That means the coefficient of time will multiply this whole term and sine will become cos. So in this case also, this sine term will become cos. So now we can see that these terms have been in common. So if you multiply with this 2, it becomes 0.02, and cos 4 pi t from here, and from here the coefficient of time will multiply this whole term 4 pi and cos 4 pi t. So after further simplification, we get this term cos square 4 pi t. So this is the expression for power delivered to the element at any time t. So if we replace t equals to 0.3 here, we'll get power delivered to the element at that particular time. So now power delivered at t equals 0.3 is given by, when we replace time here by 0.3. So after further simplification, we'll get 4 pi into 0.3 will become 1.2 pi, and this will give 164.5 into 10 power minus 3 watt. Here we have to take care, we have to be very cautious about this thing. While computing this value of cos, we have to put our calculator in radian mode because this pi is radian, and so we have to put our calculator radian mode, and we can get this expression. Finally, since 10 to the power minus 3 it's milli, so the power delivered to the element at time 0.3 second is 164.5 milliwatts. Now let's solve the second problem, part B. We have to compute the energy delivered to the element between 0 to 0.6 seconds. So energy delivered is given by integration of power. When we integrate the power between 0 to 0.6, we can get the energy. So let's say we denote energy by W, and then if we integrate expression for power from time 0 to 0.6, then we'll get the energy. So let's plug in the value expression for PT. We've computed in the previous slides. So this expression for power at any time. So here we can see that we can take this as common, also the integration, because it's not a variable, and the variable here is cos square 4 pi t. So actually we do not have any formula for integration of cos square term, so we'll use a trigonometry identity, that is cos square x equals to 1 plus cos 2x divided by 2. We'll use this identity and convert this in this form, summation form. So here what becomes is 1 plus cos 8 pi t by 2. So this expression that we got based on that trigonometry identity. Now we can separate these terms, and we can even take this 2 out of this whole term. So now this becomes, this 2 is here, and then For 1, it's dt, integration of dt, and the remaining this term, cos term, integration of cos 8 pi t. Now, in order to find the integration of this second term, for the first term, integration of dt is simply t. So, and for the second term, in order to find the integration of cos at, we know the formula of integral calculus. Cos at, integration of cos at with respect to time is sin at divided by a. In case of differentiation, coefficient of time will multiply the term, whereas in case of integration, this will divide. So it will be as a quotient term. Now replacing this, so we get this term here t. Now since this is between some intervals, we have to integrate between 0 and 0.6, and the second term cos becomes sine, and it will be divided by coefficient of time, that is 8 pi, and we have to integrate between 0 to 0.6. Now if we do so here, we have to replace value of this by upper limit minus lower limit. So upper limit 0.6 and lower limit 0. Here also we have to replace t by 0.6 and 0, upper limit 0.6 and lower limit 0, and we have to subtract these terms. After further simplification, we get this term. We get this, and after even further simplification, we get 78.34 into 10 to the power minus 3. This energy, so it's unit will be joule, so this energy will be in joule. If we want to express it in millijoules, so we'll get this. So this is how we can calculate power and energy. Now let's move to our second problem. In the second problem, we've been asked to compute the power absorbed, consumed, or supplied by each circuit element in this figure. So first of all, let's review the sign convention. We've even done this in the previous first help session. So, and the basic thing we have to remember here is when the current is flowing from positive terminal to negative terminal in an element, in that case, that element is a load or it's behaving as a load. And in that case, if that element is a load, then it's consuming power. Power will be given by I into V. But contrary to that, if the current is flowing from negative to positive terminal inside the element, then that element will behave as a source. And in that case, it will be supplying power instead of consuming. So power supplied will be given by I into V. So in this case, if you want to compute power consumed, then it will be negative of this value. So let's start in this expression. Let's see here. Let's start with this element. In this element, we can see that current 4 ampere is flowing from positive terminal to the negative terminal of this element, right? It's similar to this case. So this element is consuming power, and its power consumed will be equals to I into V, 6 into 4, 24. So power consumed by this element is given by is 24 watts. Let's see this element. In this element also, we can see that current is flowing from positive terminal to the negative terminal. So it is also consuming power. So power consumed equals to 4 into 3 equals to 12 watt. Let's see the case of source and this voltage source. In case of this voltage source, current is flowing in this direction. Since it's a series circuit, current will flow in the same direction for all the elements. So let's see. Current is inside this source. If you consider inside this source, current is flowing from negative to positive terminal, right? So this element is supplying the power. It's supplying the power, and power supplied is given by I into V, 4 into 9. So power supplied equals to 4 into 9 is equal to 36 watt. In this way, we can consume power supplied and consumed by each element. In this case, we can even see the power balance. If you notice here, total power consumed equals to 24 plus 12, and power supplied equals to 36. So power supplied will be equal to total power consumed. Let's see problem number B. In this problem, if we see this first element, it's similar to this case. Current 3 ampere is flowing from positive terminal to the negative terminal, right? So it is consuming the power. And power consumed is given by I into V equals to 3 into 10 equals to 30 watts. And let's see this element. This element might be a little bit strange for you. This is actually a dependent voltage source. The value of this dependent voltage source is 3 I naught. I naught here is 3. So the value of this voltage source will be 3 into 3, that equals to 9 volt. Value of this voltage source is 9 volt. And in this case, in this voltage source, current is flowing from positive to negative terminal, right? Although it is a voltage source, but the current is flowing from positive to negative terminal inside this source, right? So this is behaving as a load. So this is a load for our case. So since this is a load for, in this case, it's also consuming power. So power consumed equals to I into V. I here is same current is flowing all over the circuit. So current flowing is 3 ampere, and voltage, the value of this voltage source is 9, right? 3 into I naught. So 27 watts. It's consuming 27 watts power. For this element, also we can see here that current is flowing from positive to negative terminal, right? So it's also a load. It's also consuming power. Power consumed is given by 3 into 5 because of 15 watts. Here, for this voltage source, we can see that power is flowing from, current is flowing from negative to positive terminal, right? Because since current is flowing from negative to positive terminal, is supplying the power. And the power supplied by this source is given by P supply equals to 3 into 24 equals to 72 watts. Thank you. This all for first help session. Second help session. I hope I'll see you in the next help session. Thank you again.